Welcome back everybody to our radiation transfer equation, radiation heat transfer learning journal. So in the last equation, we are talking about the physical meaning of this equation, the solution to the radiation transfer equation. So all we are doing, remember, is that we are looking at the intensity from a particular angle, and you have to sum up the contributions of every of the initial boundary condition, or the initial radiation, and all the source of the medium in between. So that's all we are doing for this equation here. So now that we have that, we want to go on to solve. We want to solve for important quantities. So what are we interested in? What are we interested in when we solve the RTE? It's always important to have our goals in mind. So some typical scenario, let's say we have a solar salt kind of a thing. We are dealing with solar salt because that's usually a liquid where you have significant radiation going on. So you have CSP, right? CSP, concentrated solar power. This is one of the applications. So there is a molten salt being heated by solar power, and now it flows through a pipe and then it goes to a heat exchanger. So how does one draw a heat exchanger? So I'll just do something like that, and then okay, I think I remember now. Yes, this one. Heater or cooler. Yeah, I think this symbol will do for a heater cooler kind of a thing. So yeah, when salt flows through a pipe, hot salt flows through a pipe, it's bound to be losing some heat, right? It's bound to lose some heat through conduction, convection, and radiation. So as the salt goes through this pipe, for example, there'll be some convection that carries the heat away from the fluid to the surface, and then because the salt is so hot, radiation actually plays a role in getting the heat away from the salt to the cylinder surface, which is the pipe surface, and that contributes to how much heat is being lost through the pipe walls. So this is some of the relevant application to our radiation transfer equation. So let's say the yellow arrow is talking about the radiation heat transfer. So what are we actually interested in finding out? Well, for one, we want to know what the heat flux is. We want to know what the heat flux is at some particular point or location at the wall. We want to know what the heat flux is so that we can find out the heat loss. So heat flux is one of the important quantities we want to know. So that we begin with the end in mind. We want to solve for heat flux. Sure. What else do we want to solve for? Well, okay, first is heat flux. First is heat flux. Secondly, okay, you don't just have this this heat loss mechanism going on. Even between, let's say, in the fluid, so from like point A to point B, right? There will be heat transfer between, let's say, two different points in the fluid. Again, there'll be convection, conduction, and radiation. Okay, convection, conduction, and radiation, that will be affecting, let's say, heat transfer between 2 points in the fluid, and that we also want to take into account. And how do we begin to calculate this? We need to consider something called divergence of heat flux. Okay, what is divergence of heat flux? Divergence, if you know what the mathematical symbol is in Cartesian coordinates, is the del by del x, the del by del y, and the del by del z. Alright, del by del x, del by del y, and del by del z. Basically, what it's saying is the net outflow of heat. Right? Just remember, it's something like Fourier's law. Fourier's law. You have this divergence thing here. The heat flux equals to K nabla T. We see this triangle thing before. So if let's say you have a diffusion equation, you have del squared. So how does it look like? Okay, so this should be minus K nabla T. So for, let's say, a Laplacian equation, rho Cp del T equals to minus nabla Q, or nabla K nabla T, or if the conduction term is constant, K nabla square T. Okay, so what is the divergence of heat flux here? This is accumulation term, right? This is accumulation term. So divergence of the heat flux in this case is it is the total amount of radiation, or total amount of heat flux, total heat flux leaving the volume dV. Okay, so let's say you have a volume dV. What is the total heat flux leaving the thing? This is described by divergence of heat flux. So that's what it physically means, because you can see from this equation, this rho Cp del T, this is actually the accumulation term. How much heat is being accumulated or received into the system. That is just basically the negative of the divergence of heat flux. In this case, it is conductive heat flux. So if you want to do divergence of heat flux for radiation, the concept is similar. How much heat is lost per unit volume due to radiation. So heat loss per volume due to radiation. Okay, so these are the two important quantities we want to calculate. Okay, heat flux perhaps at the wall, and divergence of heat flux. This is within the fluid. It's the per unit volume, how much radiation heat is being given out, right? So that can help us to calculate, let's say, a fluid with the heat transfer from one fluid element to another. So these quantities are over here in part 10.8 and part 10.9 in this textbook. Okay, so yes. So we want to start, we're going to skip everything else. We want to start looking at this. So if first thing first, again, if you want to start with a heat flux, I'm going to start with how to calculate heat flux in principle. Okay, because we already have this intensity field here. This to help us solve the radiation transfer equation. This is a solution to RTE. But this tells us nothing directly of the heat flux. So how do we relate this intensity to heat flux? Okay. So again, we will need to bring up our handy dandy paint. Okay. Anyway, I'll just copy and paste this here. That's too much. I'll just leave. Maybe I'll just take up the top part. Okay. No. Okay. So there's a diagram there. There are two things we're interested is the heat flux and of course the divergence of heat flux. All right. How do you relate intensity to heat flux? That is the question here. That's what we want to tackle. So again, let's do our little diagram here. We'll have some area dA, and the heat flux equals to total power per unit area, right? Total power per unit area. And what the intensity was is actually power per unit solid angle so I'm just going to use this angular thing to denote angle per unit normal area. So a few things to highlight. You look at the denominator of here versus here. Okay, so normal area and solid angle. So how do we, at least in principle, do this? We have to convert the normal area to area first. So that is the first thing. So how do we do that? Let's say you have some intensity here. Sure, if it's at 90 degrees, this theta equals to 90 degrees. The area is just the the area is just dA, right? There's no there's nothing to speak of in terms of normal area versus the total area. But let's say you have intensity in this direction. What is the normal area? It is the projection over here. The normal area is, let me use yellow. Okay, so this is where it's going. Okay, so from this angle, all the area it sees is like this much. So I need to put a 90 degrees here, and this is dA. This is the normal area. So normal area equals to dA cosine theta. Right? So let's do this now. Heat flux equals to power per area, and intensity equals to power per solid angle, and bullet normal area. So normal area equals to the dA cosine theta. So if area is dA, normal area equals to dA cosine theta as what we said here. So I'm just going to take this, copy and paste. So normal area is that dA cosine theta, no problem. So right, how then do we change this normal area into the area? Right, so let's do energy balance. So we can say this, yeah, we can just get the net power, right? We just want a net power equals to heat flux times dA, correct? And that equals to intensity times the solid angle times normal area, right? So the normal area here is dA cosine theta. Okay. However, we also need to kind of do this integration over all the solid angles as well in order to have the same quantity at both sides. So, okay, so again, this right hand side should be as follows. Integral of I, okay, this is over the hemisphere, I d omega, so that's integrating over all solid angles, and the normal area is dA cosine theta. So let me bring this cosine theta in, right? So I need to have this quantity integral of I times this cosine theta across the whole hemisphere, and then we will have what we want. So if we were to equate this q dA to whatever this is, we can just copy and paste the integral here, and we divide both sides by dA since there's a constant, and we will have a very nice expression for the heat flux. So the heat flux is just integral of I cosine theta over the hemisphere, right? Which is simply, the hemisphere is of course over the solid angle of 2 pi, right? Okay, so, and remember, the omega equals to what? Yeah, d omega equals to sine theta d theta d phi. Remember, that's what we were doing when we did solid angles. Now, of course, the question is this theta and this theta the same theta? So I will just, for the time being, I'll just put theta prime over there. Of course, the question is theta prime equals to theta. Which theta is which? Okay, so that's one of the questions, but at least conceptually, we can see that this is the equation for heat flux. How do we get heat flux from intensity? It is like this. And of course, intensity will be pretty dependent on the on the angle with respect to the normal. Therefore, we need to put this these two indicators here to say that, okay, intensity field in general will be dependent on both the azimuthal and the polar angle. And this theta here, it is the angle from the normal, and this that will be polar angle, right? Because this is the pole and this angle is the angle with respect to the normal, or the pole, the north pole, so to speak, right? So if this theta prime polar angle, if theta prime is the polar angle, then theta prime equal to theta. So that's all. And then let's take a look whether it's the correct one. Where is our solid angle? Yeah, solid angle. So as you can see, the theta here, it is the theta in this diagram, that is also the polar angle. So this theta is the polar angle we're talking about, right? We need to refer to chapter 1.5 in Michael F. Modest's book. So basically it is, you can put this as so. I'll just put an equal sign. The other way of writing is integrate from 0 to pi by 2. I forgot the bracket there. Right, so this is the polar angle from 0, which is the top, to pi by 2, which is like 90 degrees there. I theta phi cos theta. Okay, sine theta and d theta. And phi is the azimuthal angle, which goes from 0 to let me think. Yeah, let's take a look back at the book. Yeah, it goes from this is the hemispherical integration from 0 to 2 pi. So it needs to go from 0 to 2 pi. D phi. Now just carry this whole thing in here, paste it here. Okay, so this is how we get our heat flux relation. So let's take a look at what the textbook says, just to check whether we're on the right track. Okay, so let's take a look. 10.51. So 10.51 is as follows. It says that Q eta dot n, so that is actually the heat flux, right? The heat flux is equals to, well, you integrate over 4 pi n dot ds d omega. So let's do a comparison here. Yeah, let's do a comparison here. So left hand side is basically heat flux. Okay, that is all it's saying. What we need to compare is the right hand side. So what is n dot s? N hat dot s hat. N hat dot s hat. Okay. So where is s hat? S hat is the direction of the radiation traveled. N hat is the direction of the normal. So let's always look at our diagram, because it can always get confusing if you don't use a diagram. So let's say this is dA again, and S, depending on which direction, right? S hat can be here, right? This is S hat. And remember, these are unit vectors, is n hat. So cosine theta equals to s hat dot n hat. So cosine theta is just s hat and n hat when you use the dot product. Okay. So this is something familiar. So this is where the cosine theta actually comes from. And well, instead of going across, 2 pi, which is what I was assuming, because that's only the hemispherical, intensity, they integrate over 4 pi, right? Which is actually, I guess, more correct if you were to talk about heat flux within at any arbitrary point. So okay, so that's one distinction. Okay, key points of comparison. One is that n hat not s hat is cosine theta. Two, they integrate over 4 pi rather than 2 pi. And thirdly, I think they included spectral dependence, which I kind of forgot. So you can see this, there's this lambda or this eta over here. I should have put a lambda here to indicate, oh, okay, this thing is still per spectral per unit spectrum. So let's say there's a wavelength dependence here. There should also be a wavelength dependence here if I put something like this. Okay, but otherwise the equation roughly more or less stays the same. So I just put a lambda here, or rather let me copy and paste. I put a lambda here to indicate, okay, this thing is this is depending on the spectrum. Okay, so that's something I kind of forgot. And why integrate over 4 pi? So remember, 2 pi is just taking this hemisphere. If you want to consider the net heat flux, so this is only like heat flux coming from here to here, right? Okay, so you have to kind of consider the other side as well. That's just, logic. If you want to consider the other side, you have to integrate across this hemisphere as well, coming from the bottom. So let's use a different color. Let's say you have some area dA again. So you can, if you want to do a net heat flux, not just the heat flux in this direction, you have to consider the hemisphere at the bottom as well. Right? You have to consider hemisphere at the bottom so that you have a net heat flux. Alright, rather than, just a one direction thing. So the corrected thing should be from 0 to pi, this polar angle. Okay, so now it is a more complete equation. Okay, this should be 4 pi. So that at least shows you like how to calculate heat flux from a known intensity field, right? So intensity field depending on the polar angle and the azimuthal angle, which is phi. Polar angle is theta. So that from that you can calculate the heat flux as follows. So what this equation is saying is that, okay, depending, I take the normal area and the area into account. I've taken solid angles into account by integrating across all solid angles. That's why you see this integral sign here. And you have this cosine theta, which accounts for the normal area and the difference between area and normal area. So this theta is a polar angle. And you just integrate that and you will get your heat flux. And remember, we don't integrate across 2 pi only, we integrate across 4 pi because we want to consider not just one side of things, not just the top side, we also want to consider the bottom side, so we have the net heat flux. Of course, if you want to talk about at the boundary, for example, right? So let's say we are talking about pipes in a concentrated solar power. We're talking about pipes in concentrated solar power, which is one very common application. So if we have some area element dA here at the boundary, and we want to consider the heat flux, you just want to consider the heat flux due to radiation, so we just integrate across 2 pi. Why? Because we want to consider the heat flux from fluid to surface or the boundary, right? This yellowish color thing. So there's basically no fluid over here. There's only fluid down here. So that's why you kind of just integrate all the radiation coming in. So again, in this case, how would you do it? Remember, let's say you have, same idea. We did our equation before. We take the initial radiation, and then we attenuate across it, and we sum up all the sources that are coming along this line to here. Then we'll get the intensity here at this particular angle. If we take another angle, it is over here. So again, we take this radiation, we sum up across this whole line, and then we get this intensity field here. So we do this for all solid angles, and then we'll have the heat flux due to radiation coming across on this area dA. So now if we were to substitute this whole thing in, right? The correct thing to do is to substitute this whole thing in here. This I lambda here is actually this, and if we were to substitute in, it will look pretty it looks like a monstrosity, a very sickening looking. Not sickening. It just looks very complicated. Because how many integrals are we talking about? We're talking about this integral due to we're talking about this integral due to the path length or the optical distance, and then we have another integral due to the solid angle. But what we're actually doing is, pretty simple fundamentally. In the physical sense, once you draw out all the diagrams. So this integral, remember, this is the contribution from the start, and then you take all the contributions of the medium. And of course, this is dependent on theta and phi, because, like for example, in this case, you have different optical distance that this radiation that we have to consider for each angle. So at different angles, we have different optical distance to consider. And then we have to integrate the contribution from all solid angles just to get this little heat flux thing. So that's what it physically means, and it's always good to know. And yeah. So here we have the heat flux if we integrate across all spectrum. So there's one more integral to do. But hopefully this actually helps us understand, okay, how do we calculate the heat flux, right? And what's actually going on, physically speaking. So that when we see integrals like this, we won't be too put off by it. Okay, so thanks for watching. I'll see you guys next time. Bye-bye.